Hello and welcome to this presentation on the Safe Water Optimization Tool. The Safe Water Optimization Tool, or SWOT for short, is a web-based modeling tool for generating evidence-based site-specific water chlorination targets for emergency response. Today, I'm going to go a little bit behind the analytics to show how we're taking a risk-based approach to chlorination guidance in emergencies. So why do we need a risk-based approach to chlorination guidance? Chlorination is the most widely used method of drinking water disinfection worldwide, and it's well suited for humanitarian context because it can provide residual protection against recontamination even after water has left the tap. However, ensuring sufficient chlorine residual throughout the safe water chain can be challenging. Typical practice is to monitor free residual chlorine, or FRC, after 30 minutes of contact time and then follow up at the tap. What happens after water is collected, transported home, and then stored before consumption? Even if water was safe during treatment and at the point of collection, we don't know if there will be sufficient residual chlorine at the end of the storage period. In fact, we know that chlorine decay after distribution can be rapid and significant, leading to insufficient residual chlorine at the point of consumption. Unlike chlorine decay during treatment or distribution, the rate of post-distribution decay is really challenging to predict, as it is subject to influences from the environment, behavioral factors, and source water quality. All of these are very much site-specific phenomena, and their effect on chlorine decay is not well understood. There's even more to it though, because these factors can lead to decay varying substantially within a site. This means that for any given tap-in FRC concentration, we see a range or distribution of chlorine concentrations at the household. So for the same tap-in FRC, we can see some households having sufficient FRC concentration while others do not. This means that when we try to predict the household FRC concentration, there's a lot of uncertainty. This means we need a risk-based approach generating FRC targets that consider the risk of a user having unsafe drinking water. So how do we determine these risks, and how does the SWOT address these challenges? Risk is typically measured as the product of probability and severity. In terms of severity, the general rule of thumb from the literature is that water will typically be safe if there's at least 0.2 milligrams per liter of FRC at the end of the storage period. Measuring risk, therefore, becomes a challenge of predicting the probability of having less than 0.2 milligrams per liter of free residual chlorine at the end of the storage period. And this is the challenge that we're trying to address with the SWOT. The idea for the SWOT was to develop a model that could predict chlorine decay using water quality data that was already being collected in humanitarian response. It uses paired measurements of FRC from the tap stand and the household, and as well as optional measurements of temperature and conductivity at the tap stand. This data is fed through two analytical engines: the Engineering Optimization Tool, or EO, as well as an Artificial Neural Network Ensemble Forecasting System, or just the ANNs. Both of these were recently published in leading engineering journals, Water Research and NPJ Clean Water, if you want to get the full details of these models. These analytical engines then generate a tap-in FRC recommendation for a user-defined follow-up period. So as I mentioned, the data is processed using two analytical engines. The first, the EO, is a chemistry-based model that gives really clear targets, but doesn't account for uncertainty. So every time you upload the same data set to the EO, you'll get the same result. By contrast, the ANNs are a machine learning probabilistic model, and they actually predict FRC as a probability distribution. So again, it actually directly predicts this distribution of household FRC concentrations for a given tap stand FRC. The downside of the ANNs, though, is that it's hard to get a clear target from their outputs. So as you can see, these tools really have a complementary set of strengths and weaknesses, with the EO being a bit clearer, but the ANNs being a bit better suited to dealing with uncertainty. This means that when we want to take a risk-based approach to chlorination guidance, we need to integrate these two models and leverage their strengths to overcome each model's weakness. To demonstrate what this looks like, I'm going to use a field data collected through a field trial from the Kutupalong Balokali Extension site in Bangladesh, where the SWOT project collected 6 months of water quality data in 2019. So the first step in this ANN-EO integration is to get a baseline risk for the EO model's tap-in FRC target. We do this using a retrospective backcheck analysis using the data that was uploaded to the SWOT. So for this data set, the EO target was 0.8 milligrams per liter, and it came up with this target by using chemistry principles to get a decay rate and then working backwards to estimate what tap-in FRC would be required to ensure 0.2 milligrams per liter at the household. To get the baseline risk, we then look at the collected samples with similar storage durations and tap-in FRC concentrations as the EO target, and determining the proportion of those samples that have at least 0.2 milligrams per liter of FRC at the household. So the backcheck shows that for samples with 0.78 to 0.98 milligrams per liter of FRC at the tap stand, with similar storage durations around 15 hours, 83% of samples had at least 0.2 milligrams per liter of FRC at the end of the storage period. Or from a risk perspective, there was a 17% risk of having insufficient FRC using the EO target when we looked retrospectively at the raw data uploaded to the SWOT. Now, maybe this is fine. Maybe 17% risk is great. You like the 0.8 number, good. But what if that risk is too high? Or maybe the FRC target is too high and you want to see if you can go a little bit lower without drastically increasing the risk. The EO doesn't have a way to deal with this. Again, if you upload the same data set to the EO, you always get the same response. However, the probabilistic ANN models can address these questions, and they do so by prospectively forecasting the risk based on tap stand conditions. So this figure shows the predicted risk using the ANNs for 4 different scenarios. We use these scenarios to narrow down a little bit of the uncertainty and to look at how the relationship between the risk of having insufficient FRC at the household and tap stand FRC change under different conditions. What's most important is that this is a prospective risk prediction. This is a model. The model is predicting these risk values, which makes it a forward-looking risk prediction. So let's look at that EO target again in the context of these risk figures. So here's that 0.8 milligrams per liter of FRC at the tap stand that we had previously. And we see that across our 4 scenarios, the risk ranges from 0 to 22%, with the highest risk being for the worst case scenario with PM collection. And at this upper range, this is very similar to what we saw with the EO backcheck risk of 17%. Based on this, if we want to refine the FRC target, we can look at that worst case PM collection line to either find a new FRC target based on a predefined risk level. So for example, if you wanted 10% risk, we'd read up to 0.1 on this line and then read across and down to get a new FRC target. Or if we have an FRC target in mind and want to know what the predicted risk would be, we could find that value on the x-axis and then read up and across to get the risk. So what I've shown so far deals with how we address with uncertainty in tap stand FRC targets. However, there are risks of both over and under chlorination. Under chlorination, the risks are evident. You can have recontamination, which leads to the spread of waterborne illness, but over chlorination can lead to taste and odor issues and disinfection byproduct formation. Our team and the field responders we work with on the SWOT have identified that taste and odor challenges are one of the main issues because they can lead to users turning to unsafe sources. So taste and odor is not just an aesthetic issue, it's really a water safety issue. So how do we deal with this on the SWOT? In a lot of cases, I've seen people trying to put an upper limit on chlorination to avoid taste and odor issues, but taste and odor acceptability varies within a population, so it's best dealt with probabilistically. So I'm about to show an approach to integrating FRC risk against taste and odor risk, but the data is used from an urban population, not from this refugee site, so it's really only for demonstration purposes only. Taste and odor acceptability is population site specific. So to integrate this approach, you would need to engage in some local data collection. We're working on tools for that on the SWOT right now. So with that disclaimer out of the way, this graph shows in red the worst case PM collection line that we've been using previously, and the orange line shows the risk of taste and odor rejection. And what these curves allow us to do is to look across different taps and FRC targets and understand how both of these risks change. So you can see how up to a point of about 1 tap stand, 1 milligram per liter of FRC at the tap stand, we do see drastic reductions in the risk of recontamination. But beyond that, there's very little improvement here, but we still see an escalating level of taste and odor. So you might want to use this to establish an upper limit on taps and FRC concentrations that you'd want to use. Or conversely, you might want to identify where the risks are about equal. And we can see that that's around 0.8 milligrams per liter. So there's a lot of ways you can use this depending on the pressures at your site. But what I just want to show is how we can look at both of these risks probabilistically and simultaneously. So what's next? If any of this has piqued your interest, check out the Safe Water Optimization tool at safeh2o.app and follow us on Twitter so we can keep you up to date with the latest developments as we move towards operationalizing a lot of this research. In addition, you can still sign up for the version 1 app. It's free, open source, and ready to go. Finally, I'd like to thank the team I work with. They're all great, intelligent, motivated, and delightful people. I'd like to thank our funders who make this research possible. And finally, I'd like to thank you for paying attention, and I look forward to any questions that you might have.